Good morning, everyone. My name is Sciancalepore. I am an assistant professor at the Eindhoven University of Technology, and today I will introduce you our work, namely FRACTAL, single-channel multi-factor authentication through a compromised terminal. This is a work result of a collaboration between the Eindhoven University of Technology and the Hamad bin Khalifa University College of Science and Engineering in Doha, Qatar. This is the agenda of what I'm going to talk to you about. I will first introduce the problem and the motivation of our work, to then go over the threat model and introduce you to the fractal protocol suite addressing the threat model discussed before. I will also quickly go over the security analysis of our solution and then introduce you the experimental performance assessment we carried out thanks to the implemented proof of concept. Finally, I will go over the conclusion and the future work and vision for this particular work. The problem we tackle in this contribution is the problem of the security of online banking services. Any one of you today basically interact with the online banking services online thanks to PDAs, laptop, computers, whatever mean to connect to the internet. And typically the first step is to carry out authentication, and this is performed via multi-factor authentication. This multi-factor authentication is typically multi-channel. This means that you use not only the internet channel, but you also typically receive an SMS on the mobile registered with your banking service, and you are requested to type this SMS typically in a page. Alternatively, you could use an app or a token. If the internet channel is not available, typically banking services rely on dedicated PIN generators, by which you can basically demonstrate to the banking service the fact that you have the possession of the card. This is what usually happens when authenticating with these online banking services. However, there is a gap both in the current research literature and in the solutions currently used by these banking services, and this gap is related to a situation where the user is interacting with the bank by using a single channel via a possibly compromised terminal that has no additional internet connection. In particular, this is the case, for example, of aircraft, cruise ships, or places in holiday resorts that are typically far from the land and so disconnected from the internet. In that cases, you typically don't have a connection with the mobile operator, so you cannot receive an SMS via the mobile cellular network. If you also don't have your PIN generator available, typically for you, it's impossible to carry out the authentication with the banking services, and simply you cannot use the service. Why? Because if your single device, the primary authentication terminal that you are using to interact with the bank, is compromised, the overall security framework used for this interaction cannot assure you to be able to carry out an authenticated transaction. So the research gap that we address in this contribution stems from the main questions that are listed here. That is, what if the untrusted terminal, that is the only terminal equipped with an internet connection in this context, is compromised by an adversary? How can we ensure transaction authenticity and detect as well as reject impersonation attacks in this scenario? This is the gap that we are going to address here in this contribution. Let me wrap up on the scenario that we assume in our work. We have a user that we call A that is interacting through an internet connection with the remote banking service B. This interaction happens on an SSL/TLS secure connection. So the connection between the PAT and B is theoretically secure. We have also additional authentication terminals besides the one that is used by the user to interact with the banking service. These additional terminals can be the mobile cellular devices or IoT devices. They are general purpose devices. They are connected to the primary authentication terminal of the user only via ad hoc links that can be, for example, a Bluetooth connection, and they have been previously registered by the user with the banking services, so they are known to the banking services. In this particular scenario, we want to verify to ensure transaction authenticity between the user and the banking service. In this context, the adversary model that we consider is an adversary that is in line with the famous Dolev-Yao attacker model. The Dolev-Yao attacker model is based on the fact that the adversary can listen all the incoming messages, and it also has active capabilities, so it can inject and forge new messages on the fly. An additional capability on top of the Dolev-Yao attacker model that we give to the adversary is the full control of the path. So the PAT, the primary authentication terminal that is used by the user to interact with the banking services, is fully compromised by an adversary. The objective of such adversary overall is to modify a legitimate transaction. This can be done by changing the destination or the amount of the transaction in a way to redirect a particular amount to a different server that can be used to carry out a man-in-the-middle attacks. We also consider two different ways of carrying out these attacks, synchronous and asynchronous. The synchronous way is the one where the adversary modifies a legitimate transaction initiated by the user, so it waits for the user to initiate the transaction. In an asynchronous scenario, instead, the adversary starts the transaction without having to wait for the legitimate user to be online. We will address both of these scenarios in our work. To address this specific scenario, we introduce the protocol flow FRACTAL. FRACTAL is basically divided into two main steps. The first one that is agnostic of the particular communication technologies at the additional authentication terminals. And the second one that instead depends on the technology used by the PAT to interact with the AATs. Let's start with the initial part. FRACTAL is basically triggered as soon as the mutual authentication of the SSL-TLS protocol ends. The mutual authentication is something that is not related strictly to FRACTAL, and typically it involves the exchange of X.509 certificates over the SSL-TLS connection. As soon as this procedure is completed, then the through the PAT, the user delivers the destination and the amount for the transaction. At the request of this information, the banking service generates what we call a passcode C that is encrypted through the public key of an additional authentication terminal. Specifically, this group of operations that you see listed as 5 in these slides are executed once for each additional authentication terminal that the user wants to use to verify the transaction. We generate the pseudocode on the banking service. The banking service encrypts it with the public key of the additional authentication terminal, generate a string comprising the destination, the amount, the timestamp, and the encrypted passcode, and signs this particular element by using its own secret key. These two values, gamma and delta, are then delivered to the primary authentication terminal that can verify the authenticity of the received message. The values, destination and amount, are shown to the user at the step 8 just to verify visually that what you input is what you get for the transaction. The following step depends strictly on the specific communication technology that you have on board of the AATs. Let's first consider the case where the primary authentication terminal and the additional authentication terminal can communicate over the air, for example, through a Bluetooth connection. The PAT delivers to the AAT the values received from the banking service, so gamma and delta, and the AAT can immediately verify the signature, delta, because it possesses the public key of the remote service, and decrypt the passcode using its own secret key. The values that are received from the banking service, so destination, amount, timestamp, and the passcode, are shown to the user that, again, can verify, this time by looking at the additional authentication screen, the fact that the values that he input are the same values that are being used during the transaction. To make it explicit its consent to this particular transaction, the user can insert the passcode C on the additional authentication terminal. This is a feedback about the correctness of the exchanged information. The additional authentication terminal then encodes this value in a string that we call gamma, that is a signature of the passcode, the destination, and the amount using the public key of the additional authentication terminal and delivers this value that we call this time lambda to the primary authentication terminal, whose only task now is to forward gamma and the previously received delta to the online banking service. The online banking service here simply verifies that all the details match, so the destination and the amount are the ones that were previously input by the user, and the passcode generated for this transaction match. If all these checks are verified, the transaction is authorized, so there is a success. If anything instead do not match, the transaction is. The second scenario that we considered in our paper is the scenario where the primary authentication terminal and the AAT cannot directly communicate with each other, so we have to resort to an alternative communication channel that is offered by the QR code. So when the primary authentication terminal and the AAT cannot be paired, for example, through an internet connection, the PAT encodes the information that it needs to send to the AAT in an image, in a QR code that is acquired thanks to the camera on the AAT. Then the flow is basically the same we saw before. So we decrypt the signature, we verify the signature, we extract at the step 4 the passcode, and we show to the user the destination, the amount, the timestamp, and the passcode. Again, the user verifies the match with the values he inserted before, types C as an acknowledgement of the correctness of the transaction at its own side, and then these values on the primary authentication terminal are delivered to the banking services, so the passcode and the delta that was previously generated by the remote service. The difference here is that the code is input on the primary authentication terminal and not on the AATs, because the AAT cannot communicate back to the primary authentication terminal. In this way, we can carry out this verification, this strong authentication, even when the AAT and the PAT cannot directly communicate with each other. As for the security considerations, in the paper we included a formal security analysis of our approach. In this presentation, I will skip that formal part and I will focus on a different kind of security, of formal security analysis. That is the one we carried out through ProVerif. ProVerif is an automated security protocol verification tool that uses the Dolev-Yao attacker model, so it's feasible for modeling our situation here. In particular, to model the compromise of the primary authentication terminal, what we did is to make public the key that is used to secure the link between the primary authentication terminal and the remote banking service. In this way, being this key public, anyone can impersonate the primary authentication terminal and so interact with the remote service by pretending to be the primary authentication terminal. That is exactly the scenario that we are tackling in this paper. Remember that ProVerif do not focus on the security of the cryptographic functions. That is, it does not assume that you can break the hash, but it assumes that this particular cryptographic functions are secure, and it focuses on the logic combinations of this security function. We verified by implementing the protocol in ProVerif that even when the key that is used to secure the link between the PAT and the remote banking service is leaked, that is highlighted by the first string in this box here, query not attacker, TLS key is false. Even in this situation, what happens is that, as shown in the second line of this verification summary, whenever the transaction completes X successful, effectively, really, it was initiated by the remote user. So this is exactly what we were discussing here. We are able to ensure that the user is able to authenticate with the remote service. That was exactly our aim. We implemented FRACTAL as a real proof of concept by using well-known tools. In particular, we used the Spring Development Framework for the client-server implementation. We used MongoDB for the transaction management and databases, the well-known OpenSSL library for cryptographic-based tool, ZXING for image processing for the part related to the QR code, and finally, for the app development, we used Android Studio. So all tools that are widely available on. In this slide, you can see some screenshots of our applications at work, in particular the application working with the Bluetooth scenario. You can see in the leftmost part of the slide the details that are shown to the user as to allow the user to verify the match of the details he inserted before with the transaction that is being executed. So the timestamp, the destination, the amount, and the passcode. In the leftmost part of the slide, instead, you can see the box where the user can insert, for example, on the laptop, the passcode that he is seeing on the particular client. We also carried out a preliminary performance assessment of our solution. In particular, the problem that we had here was that we couldn't deploy our server on any of the available cloud farms available in the internet. So we could not deploy it on a specific server available on the internet. The way we found to model the end-to-end delay with interacting with the specific server was to issue a chain of echo requests to several IPs located on the internet in several different locations in a way to create a distributions of the end-to-end delay in interacting with a particular solution. Of course, you can have a server that is located closer to where you are or a server that is located farther. And the delay in carrying out the authentication procedure to Fractal is strongly affected by the delay with interacting with the specific location where the server is deployed. We then used these particular results to obtain results on the delay that you experience when you want to complete a transaction. The results are reported here in this slide. If you see in the leftmost part of the slide, you see that, as expected, the delay in interacting with a particular server is given by the specific location of the server. However, even in the worst case, we were able to complete a transaction, including the authentication carried out with Fractal, in slightly less than 2 seconds. So the solution is definitely usable, and it is basically only affected by the delay with interacting with the server. At the same time, also the number of additional authentication terminals that you use slightly affects the delay that you experience, because you have to carry out a validation of the information on each AAT that you use. And the more AAT you use, the more secure your solution is. The graph that you see on the right shows that basically even when you use 5 AATs, approximately in 4 seconds, assuming they are all Bluetooth links, you can complete your transaction. And this is not so different from the 3 seconds that you experience here with 1 AATs. So in general, the solution is also. So wrapping up, we presented Fractal, a protocol suite for single-channel multi-factor authentication that is able to ensure transaction authenticity also when the path is compromised and you don't have any access to the mobile network and to any other additional internet channel than the one that is used by the path to interact with the remote service. Fractal also uses general-purpose additional authentication terminals, for example, mobile and IoT devices for this purpose, and approximately it can complete in approximately 2 seconds, so quite lightweight. For this particular design for Fractal, we also submitted a patent application to USPTO that is pending approval. And based on this, we also expect to be able to license and commercialize our solution. There are already some partners interested. As for the research aspect, we are working on the extension of Fractal to other domains beyond the banking service. For example, military is one of these. And we also want to compare more in detail our solution with the ones offered within the FIDO and FIDO2 protocol suites that are now under development by Microsoft and all Amazon and all the other alliances available worldwide. What we know at this time is that they don't appear to address specifically our scenario, but we want to investigate this more in the coming future. That's it for this presentation. Should you have any questions, I am here to take and reply to your questions.